Okay, everybody. Hello. All right. So, sure enough, here's another example where there's a lot of little steps to doing the math to calculate things like effective temperature. So having your spreadsheet to do all the math for you certainly makes understanding the answer much easier. And if you do it right, hopefully less getting lost in the weeds. So, all right, let's look at this first question here. For all three of the properties below, highlight the choice that would produce a warmer planet. So would you have a warmer planet if you were around a high luminosity star or a low luminosity star? Well, if your star is putting off more energy, then that planet's going to get more flux shining on it, so the planet will be warmer. Would you have a warmer planet if you were orbiting at a large orbital distance? So in other words, would your planet be warmer if you were far from the star or close to the star? Well, if you're orbiting with a small orbital distance, right? If there's a short distance between the star and the planet is close to the star, you're going to get more flux again and a warmer planet. Albedo is a little tricky though, right? Albedo is how reflective the planet is. If the planet, if you've got this planet, if sunlight shines, or starlight, right? If light shines on the planet and the planet just reflects that light back out into space, then that light doesn't get absorbed by the planet. And if the planet doesn't absorb the light, then it can't be warmed by it. So a high albedo planet is one where more light gets reflected, less light gets absorbed, and therefore there's less heating. So a high albedo planet is a cooler one. A low albedo planet means the light comes in, less of it gets reflected away, and if more light comes in and less light gets reflected, then more of that light is going to get absorbed by the planet, and if the planet absorbs the light, then the planet will warm up. So a low albedo planet is one that will absorb more light and be warmer. Okay. So then we got these two formulas here, right? In order to get the effective temperature, we need to know the flux and the albedo. How do we figure out the flux, though? The flux of starlight shining on the planet is the luminosity divided by 4 pi radius squared, or 4 pi distance squared. The orbital distance, orbital radius, same thing. But the flux needs to be in watts per square meter, just like the flux we've been dealing with all semester. Which means we need to convert the luminosity from solar luminosities into watts. We need to convert the orbital radius from AU into meters, and then we plug those in here to get the flux. So that's our first step. Right. And since I've already got the spreadsheet to do this for us, let's see what kind of answers we should be getting. All right. So if you have a star, if you're a planet orbiting a 1.5 solar luminosity star, well, 1.5 solar luminosities is 5.74 times 10 to the 26th watts. If that planet is orbiting 2 AU away from the star, then that planet is 2.99 times 10 to the 11 meters away. And therefore you take the luminosity in watts, the distance in meters, and calculate the flux. So this planet, and again, the flux should be, I guess we could fill this out, right? The 5.74. All right. So, I guess I could have this do the math for us. 4 pi r squared. I'm just gonna label it that, right? So 4 times pi times the orbital radius squared will be, okay, go back up here, 5.74 times 10 to the 26th watts divided by, and this will be in units because we're taking the radius in meters squared. This will be in units of meters squared. So that's 1.12 times 10 to the 24. And again, you got big number divided by, oh, that's meters squared. So you got big number on top divided by big number on the bottom. So when you divide them, your flux should be not too big of a number. The kind of flux you're looking for is hundreds to thousands. You know, for a cooler planet, that would be a flux of hundreds of watts per square meter. If you got a hot planet, it might be 1,000 or 2,000 watts per square meter. But yeah, your numbers here should be in the hundreds or low thousands. And you know, I'm just going to move this around to make this cleaner, make it nicer for me. Okay. Right, so that's a flux of 510 watts per square meter. And if you have a planet receiving 510 watts per square meter, and it has an albedo of, what are we told here? 0.5. Okay, so that planet reflects 50% of the light shining on it, which means it absorbs the other 50%. Then, with an albedo of 0.5, all right, that, I'm not going to fill this out. Hopefully you did, as a way to keep track for yourself. But that has an effective temperature of 183 Kelvin. So that's a pretty cool planet, right? It is, you know, this planet is orbiting a brighter star. This star is brighter than the sun, but the planet is also farther away than Earth is from the sun. So which of those, you know, is the planet hotter than Earth because the star is brighter, or is it cooler than Earth because the planet is farther away? And it turns out that, yeah, the effective temperature is 183 is, yeah, that's pretty cool, right? Room temperature on Earth is about 300 Kelvin. So that's a chilly planet. Will this planet have liquid water if the atmospheric pressure is 1 atmosphere? Well, let's look this up on our water phase diagram. All right. Let's see here. So, let's see, 150, 60, 70, 80. So 83 is going to be right about there. All right, 180 Kelvin, 183 Kelvin, and follow this line as close as I can. All right, they're at 1 atmosphere, right? 1 atmosphere of pressure, 183 Kelvin. That planet's going to be right there, which means any water on that planet is going to be frozen. Okay. Suitable for liquid water? No. Too cold. Okay. How about this one? And we've already got the spreadsheet to do all the work for us, so I'll move this down some more. All right. Kepler 440b is a point. So Kepler 440 is the name of the star, and then B represents the planet. So Kepler 440 is a star with a luminosity of 0.14 solar luminosities. Kepler 440b is a planet that is orbiting at a distance of 0.242 AU, and it has an albedo of 0.3. So this is a dim. So if you're eyeballing these numbers, what can you expect? What do you think? Well, this is a dim star, but the planet is orbiting really close to it. So is that planet going to be too hot, too cold, or just right? Well, it's a dim star, but you're close to it. So maybe this planet is just right. Maybe it's nice and warm and temperate. How can we know for sure? Well, let's do the math. Okay. Have our spreadsheet do the math for us. The flux of starlight shining on this planet is 3,250. I'm just going to round up to 3. So again, a flux that's in the, low thousands like we were expecting. That sounds like a warm planet. With an albedo of 0.3, we have an effective temperature of 316.5 Kelvin, which is, like I said, room temperature on Earth is about 300 Kelvin. So 316 is, a little warmer than Earth. What would the water be like? Well, life easier there. 316 Kelvin's right about there. 316 Kelvin in 1 atmosphere. All right, that planet is going to be warm, but still able to have liquid water. Well, I guess it's just over there. But all right, so that's a little warmer than Earth, but not too warm. It can still have liquid water. So if there's water on this planet, it's probably warm but still liquid. So that's exciting. If you're looking for a habitable world, this one might be worth spending your time studying more to see, is there liquid water on there? And if there's liquid water, what else could we have? Could there be life down there? That would be a planet. The first planet we were studying that's too cold for liquid water, if you're looking for life in the universe, that's probably not a good place to study. This one, that one is maybe worth some follow-up to see, well, are there other possible signs of habitability on Kepler 440b? How about Alpha Centauri BB? Let's see here. All right, Alpha Centauri B has a luminosity of 0.787 solar luminosities. Alpha Centauri BB is orbiting really close, 0.04 AU, and has an albedo of 0.2. So that's going to be getting a flux of 669,329. Let's see here. We got 3 significant digits here. We got 1 significant digit here. I don't feel that bad about just stopping there and saying, all right, 669,000 watts per square meter. That's a pretty big flux, which would make you expect that's a pretty hot planet. Then you calculate the effective temperature, and you're getting 1,239 Kelvin. What's water like at 1 atmosphere, right? At 1 atmosphere, water, let's see. At 1 atmosphere, water freezes at 273 and it boils at 373. So this is well above the boiling point for water under 1 atmosphere of pressure, which means this is not suitable for liquid water, way too hot. How about Venus? All right, well, Venus is orbiting around a 1 solar luminosity star, obviously. It's orbiting at a distance of 0.72 AU, and it has an albedo of 0.9. So that's a flux of 2,625 watts per square meter, an effective temperature of 184, and 90 atmospheres of pressure. So 184 Kelvin, but under 90 atmospheres. What is water like under those circumstances? So 90 atmospheres, well, 90 atmospheres is just a little under 100, and 184 is right about there where we were looking at that first planet. So 184 Kelvin, 90 atmospheres of pressure, so Venus would be right about there. The water will be frozen, which is weird, because we don't see ice on Venus. Right? Is it suitable for liquid water? No, the water should be frozen. We got a problem. Right? The effective temperature says any water on Venus should be frozen, except that when you look at Venus, there's no ice, there's no liquid water. Venus is too warm in actuality. Right? Venus is too warm, and any water on Venus boiled away a long time ago. Like I said before, the effective temperature of a planet is a good first guess. It's a good estimate for what the temperature of the planet could be. But it's not the whole story. The good first guess for Venus is that the water should be frozen, but it's not. So clearly we need some more detail, right? Clearly this effective temperature model is not sufficient to explain the actual temperatures of planets. It's a good first guess, right? The effective temperature is a good first guess, but we need to add some extra details to figure out what the real temperature is, which is what we'll be getting to here shortly. But in the meantime, all right, what about Mars? Here's my spreadsheet. All right. Mars orbiting a one-solar luminosity star, sure, 1.52 AU away, an albedo of 0.24. Okay, so Mars is receiving 589 watts per square meter of sunlight, of the flux of sunlight, and an effective temperature of 210 Kelvin. What's water like at 210 Kelvin? 210 Kelvin is here. What was the air pressure again? What was the atmospheric pressure? 0.007. So let's see, if this is 0.001, if this is 0.001, 2, 3, 4, 5, 6, 7. Okay, so an atmospheric pressure right about there, 210 Kelvin. Go up to right about there. All right, so Mars is right about there. The water's frozen. Liquid water? No, it should be frozen. And actually, when you look at Mars, it is frozen. Okay, so this model here works okay for Mars. What about Earth? Earth is orbiting a one-solar luminosity star. Earth is orbiting the sun at a distance of 1 AU. Earth has an albedo of about 0.3. So the flux of sunlight on the Earth is 1,360 watts per square meter for an effective temperature of 254. The freezing point of water is 273 Kelvin under 1 atmosphere of pressure. So, based on the water phase diagram, does Earth have the right temperature for liquid water? No. At 254 Kelvin, the water should be solid. So, again, we have a problem, kind of like we did with Venus. Obviously, most of the water on Earth is liquid. The oceans, the lakes, So the effective temperature predicts that the Earth is too cool for liquid water. Can you think of a way that you can account for this discrepancy? Why does the Earth have liquid water when the effective temperature says it's too cold? Why does Mars have the water frozen, but the effective temperature says it should be frozen? Why is Venus so hot that the water has all boiled away when the effective temperature says that the water should all be frozen? And the answer is that atmosphere. And a planet's atmosphere is also good at holding in heat. Right? Venus has this really thick atmosphere, 90 atmospheres of pressure on Venus. And with that big, thick atmosphere, that atmosphere can hold in so much heat that it heats up Venus a lot more than the effective temperature predicts. Right? That's why the water's boiled away and not frozen. Mars doesn't have that much atmosphere. And so Mars's atmosphere doesn't hold in that much heat, which is why the effective temperature is pretty close to the actual temperature. The effective temperature says the water should be frozen, and it is. Earth's got 1 atmosphere of pressure. Not as much as Venus, but it's enough to warm the Earth up a little more. Right? 1 atmosphere of pressure is enough to warm up the Earth by about 30 degrees. And at 30 degrees, the Earth's atmosphere warms up Earth by an extra 30 degrees, which makes the temperature about 284 Kelvin, warm enough that the water can melt. That's why the Earth can have liquid water, is that it's the effective temperature plus the extra heat held to the Earth by the atmosphere. That's what warms up the Earth a little bit, making the Earth a nice, warm, comfortable, temperate place, warm enough for the water to be melted. What do we call that? What do we call that effect where the atmosphere of a planet can help warm up the planet a little bit more? That's what the greenhouse effect is. Right? The greenhouse effect is the effect where an atmosphere can hold in heat, warming up a planet more than what the effective temperature model would predict it should be. Right? Planets that have little to no atmosphere aren't going to have a very strong greenhouse effect. It's not going to warm up the planet by very much. Venus has such a thick atmosphere that the greenhouse effect is super strong, and the greenhouse effect heats Venus up from 184 up to like 750 Kelvin. What's water like at 750 Kelvin under 90 atmospheres? It's boiled away. The thicker the atmosphere is, the more extreme the greenhouse effect can become. Earth's got a little bit of an atmosphere, so we get a little bit of greenhouse effect. Venus has a thick atmosphere, so it gets a lot of greenhouse effect. So these 2 exoplanets, if they have 1 atmosphere of pressure, then we might expect there to be some greenhouse effect here too, right? These, 316 Kelvin, 1200 Kelvin, this is what the effective temperature predicts as a good first guess. But we know when a planet has an atmosphere, it's going to have some amount of greenhouse effect. So we would expect. Do we know for sure what the temperatures of these planets are? No. It's hard to see these planets. These are exoplanets. These are light years and light years away, right? It's hard to see the planet to know what the real actual temperature is. We'll probably be able to do it soon, but we don't have the technology to do it quite yet. So what we can expect is, given if these planets have an atmosphere of pressure, they're going to have some amount of greenhouse effect. So whatever the real temperature is, we can expect it to be a little hotter than those. How much hotter would require us to figure out how strong the greenhouse effect is, and that's something that we can do, but that's a story for another day. Say the effective temperature is a good first guess, knowing full well that we need to figure out how strong the effect of the atmosphere is going to have on adding some extra heat to the planet. Okay. Yeah. Like I said before, having the math, having the spreadsheet already programmed to help us out with that certainly makes life a lot easier here. So hopefully that makes sense. If you need some help or have some questions, post to the discussion or come into office hours. Until then, let's talk about some more atmospheres. All right, on to the next thing. Take it easy, folks.